Hello, everyone. In this video, we're going to talk about discrete and continuous traits within a population. So we'll be talking about, how traits actually move through the population, sort of what patterns do we see, and how do they actually form phenotypes. So I'm going to do a screen share here of PowerPoint that I have stored. Here we go. All right. All right, so we should know by now that there are two different types of traits that we see out there, monogenic traits, and that's where we have one gene, one effect. And so that means we just have, two alleles come together, they're going to produce, one sort of effect or the phenotype of what the appearance of an organism is. And then we have polygenic traits, where it takes many different genes, different loci, that come together to produce a trait. And think about polygenic traits. We can provide continuous variation that way. In other words, we can generate more variability. And as far as from evolutionary perspective is, the more continuous variation that you produce, the better off it is for an organism in general. Thus, we're going to see more polygenic traits within life forms than we are going to see monogenic traits. Now, of course, monogenic traits were things in which Mendel was looking at because they're easier to track, easier to formulate, to sort of understand the underlying rules. Once you have the underlying rules, you can apply them to polygenic traits. It becomes more complicated from a visual perspective, using Punnett squares when we're dealing with multiple effects, with genes that come together to produce the trait. So that's why we don't start with monogenic traits. Now, as far as polygenic traits, we're going to try to understand some of the basics, but we're not going to be tracking these things, through Punnett squares or by mathematics. We just want to get some of the underlying principles. Okay, so for polygenic traits, we know, it takes multiple genes for one effect. Well, what sort of things do we see these produced, like in the human body? Well, stature for one, height. If you notice, people don't come in just block sizes of 3 feet, 4 foot, 5 and 6 feet sizes. There's a continuous variation. And if I lined you guys all up, you see that variation in the classroom. And, that's important because, humans, size does matter in the world. Not so much in our modern world. I mean, it isn't, your stature relatively doesn't really define, what you can do. But on many degrees, we find out lifespan is influenced by stature in many conditions. Some sorts of occupations are too influenced by stature. And if the occupational needs of humans change over time, so might the stature requirements, which might mean a fine gradation, to hit that target sweet spot. Skin color too. So there are many genes that go into actually producing skin color. And we'll be looking at those as well as eye color too. These are the simplest ones that we can actually see. Skin color, eye color, and height are the most visible to us. But of course, you're looking at 23,000 plus different traits that go into building the body, and they're combinations of, phenotypic or polygenetic traits that go into producing humans and a small amount of monogenic traits. We can't cover all of those bases. We'll use those three here, I think, as good representative types. All right. So skin pigmentation, a great polygenic trait. Look at it, 34 different genes have been detected to influence skin color. It might actually increase, and likely there's probably 100 that go into this, but 34 solidly. When we talk about that, look at the 34 we can put together and all the different sort of genotypes that combine to create all the different sort of phenotypes we have in skin. So there are at least 69 different phenotypes or 69 different recognizable skin colors among human beings, which is sort of interesting to think about. And, the way people sort of box people into terms of color, they got the black, brown, the white, the whatever color you have out there. But in reality, there's a pretty good sepia rainbow of skin types. So people who do that are relatively uneducated. I was still ignorant, and I walk around looking at people and these sort of phenotypical blocks like that, and I know where I sort of sit in. I'm between this about a number 6. It's sort of my look at my skin color. I'm not translucent, my mom's really translucent. These Scandinavians, she's like number 1, right? So, my dad's like number 15. So 15 to 1 is sort of phenotype I got together, makes me in sort of the 6 range. At the very bottom, you can see the number of phenotypes and the frequency in which they spread out. And that's the interesting thing about this stuff, is that if you look at the very bottom little band down there where you see the numbers, that represents the ratio that you're going to see among all these 69 different phenotypes out there in the world. And you look at the very extremes here. So you see number one, we have super dark skinned people, and we have number one on the other side, and only one of those among the ratios of super light skinned people. And that reflects the amount of individuals that need to have these things, depending on where we live proportionally across the globe. So my ancestors, most of my ancestors migrated, out of Africa very quickly, within a 30,000 year period up into the northern extremes of Europe. And the problem with that is that we'll find out here, we're watching a film by Nina Jablonski next, is that skin color has a lot to do with our vitamin biology, vitamin D biology, and as well as a lot has to do with our success ratio of keeping skin cancers and vitamin folate depletion. So my ancestors went north to the higher latitudes. What happened was my skin, through differential reproductive success and change of allele frequencies in a population, which is the definition of evolution, lost many of the alleles for darker skin in the population and began to increase the number of alleles for light colored skin. And because at low UV light levels, I need skin which will take in more UV radiation to catalyze the synthesis of a vitamin D precursor called cholecalciferol. You don't need to know that. And it catalyzes that reaction to make vitamin D. We need sunlight to power sunlight. The body can't do that final trick. So that's the way in which I get vitamin D, right? So I need to have that. But at the same time, I'm so high in the UV radiate belt, it's so low that my skin can actually be, light like this, and I won't get that much UV damage. And not only to cause a skin cancer, but also the depletion of a very, very vital cofactor called folate. And folate is very important in cellular reproduction and cellular function, and UV radiation will destroy it. Now, on the other spectrum, look at number one, guy on the other side. Okay? This is guys that we find in Melanesia, where we have some of the highest UV radiation levels in the entire world. Well, this fellow here has a problem because he'll get his folate damaged and skin cancer unless his skin is very dark. So dark color. But also because there's so much UV radiation, there's still enough to get through, even with dark skin, to cause a chemical change, a chemical reaction that creates vitamin D, right? So everywhere in between represents the proportion of people that live in other environments. So my ancestors, only a few of us went north. It was a stupid thing to do. There's no food up there. It's cold as hell. My ancestors went so north and northeast. Why they did that? But a very small proportion of people live up there or evolved up there in their lines. Thus, that represents the proportion of that phenotype which is needed, in the population. Of course, the corresponding genotypes that come together. But look at number 20, the folks right in the middle, the proportion of higher number 20. Those would be things by people live in Southeast Asia. Maybe current day Mexico, all the way down to, maybe Ecuador. That you're looking at people that are living in that sort of not super high UV light, but consistently high UV light, that need to have just about that skin color, the optimum for protection against UV radiation and to facilitate vitamin D conversion. So, because the broad perspective, the proportion of people live in that belt, and that's where all the food is, and where it's warm, rational people would do that. We have the largest number of genes that come together to produce that phenotype. Okay, so this shows us the evolutionary sort of reasons why we have the skin colors we do, and also why it takes 34 different genes, because we require all those different phenotypes because of the gradation of UV radiation in different latitudes. Okay, classic example of a polygenic trait. So I want you to move ahead now at this point to look at this video by Nina Jablonski. She's probably one of the leading experts in the world on skin color and evolution. You can access it. You can't from here because this is a PowerPoint, over Zoom, but on your own PowerPoint, which you download, you can click on that or actually have this film embedded in the assignment window too. So you click on it directly, but I want you to watch it. It's a short one, it's only 15 minutes. It reiterates everything that I said here, probably in a better way. I love Nina Jablonski. She's highly energetic and very entertaining. So I hope you enjoy it. Okay. All right, so, eye color too. Let's address eye color. I think it's important that eye color is polygenic. There are probably at least 15 genes that go into coloring eyes. Many of these genes, of course, are in systems of dominant and recessive conditions. So when you bring genes together, remember within those genes too, each one of their dominant recessives to each other in 15 different combinations, right? So when you bring these combinations together, they can produce an incredible variety of eye color. There aren't just brown eyes and blue eyes out there. There's incredible amounts of shades when you look into somebody's eyes, right? They may be towards more shade than the other, towards more shade than towards the other sort of shade. But there's a huge gradation in between, right? It's because humans just love to lump things together. They miss the subtle nuances, which are extremely important, right? So when we look at what all these 15 color, eye genes come together polygenetically to produce this one trait, look at the sepia rainbow eye colors that we have out here, and they're actually more than that. So if you can sort of spot yourself in there somewhere, you'll find out there will even be probably differences between what you're seeing in this chart and what your eyes actually are. You probably have some differences in what's here because the phenotypic spread is much larger than this. That can be that because the amount of variation provided by those 15 different genes. Now, when we think about these polygenic control of eyes, those 15 genes aren't stagnant within a population. We have to remember they're always changing. So, there's a chance that as I'm breeding right now, well, not anymore. I don't want too much money, but my children will someday. That they're going through meiosis, and then these genes are being replicated, and there could be changes in these genes. Changes in these genes to be passed down to their kids' generation, which can bring in new alleles into a population. And as new alleles come in, they could be more successful. So we could have more combinations of eye color in the future than we see right now. And certainly since the arrival of humans, 100,000 years ago, these genes have changed. So highly likely, if you went back 100,000 years ago and looked at humans, you would see different variations in eye color than are present in the population. One thing you aren't going to see are the blues, most likely, because all humans evolved in a high radiation belt in Central and South Africa. So the blue addition, the new alleles, have been brought in since our migration. So you can see the change in allele frequency in populations that that allele has actually increased. And we can look at genetic evidence of that later when we look at ancient human DNA, trying to find those alleles for blue eyes which don't exist, and we can see exactly when they start coming in. Now, where they're going right now, we don't know. Humans are living in all sorts of different environments now that we're not used to. And we have all sorts of different sort of cultural inventions that change selection pressures on eyes. So my lovely blue eye color here, is somewhere probably in the top row over at the top, over to the right-hand side, that sort of blue. That's sort of me right there, the top, up here category, second column in. So when I look at sort of that sort of, texture in my eye, I'm realizing that I'm not at disadvantaged anymore against people who might have a dark brown color. I don't. Simply because when I go outside to drive my car, if I didn't have sunglasses on, I might hit another car because of glare. I could, and then it eliminates me from the breeding pool, and through, differential reproductive success, and not only that, but it's elimination of me, and therefore I'm not going to pass my alleles on. My allele frequency, blue eyes will decrease, and brown eyes will increase, but not anymore because of sunglasses. I can wear my sunglasses and I have an equal advantage to people with brown eyes in lower light latitudes. So, where are we going to get an increase in blue eyes? Depends. I think what happens is we're getting to the point right now where cultural preferences are beginning to drive selection pressures right now. The aesthetics of what people think looks better, continually has more people mate with those traits. And I think people are designing ourselves, we're actually breeding ourselves, to look a certain way versus having nature select this out in and out because we fit to the environment. So they'll be interesting to see what humans actually do because of our cultural sort of drives, in the next 10 to 20 to even 100,000 years. But then again, that depends on cultural values at the same. They're always changing. Think about body size, right? It used to be big bodies, for women, very curvy. All this stuff was super beautiful, popular, and all of a sudden all that went away to super skinny, and all of a sudden it's starting to come back to a middle line, which is more muscular now. More women want more curve and muscularity. So all those cultural values change. So even though we're trying to self-select in our own choices for mating choices, will these hold up to change the allele frequency in our population? Probably not, because our cultural values are constantly changing. That's my opinion on it. All right, let's move on. All right, so we've looked at the difference between monogenic and polygenic traits and looked at it in two very simple examples, eye color and skin color. But then remember, there's hundreds of other, like timing of puberty, all these other things, biochemical process that happen in you. There's lots of continuous traits. And we have to remember there's very few monogenic traits. Many of those you can see in your body already, with people that can wiggle their ears or they can't. People can roll their tongue and they can't. And generally where we see monogenic traits is a lot of times it really doesn't function so much as for your success. It's sort of a moot point. Like, I don't think the ability to roll your tongue or not is going to change my ability to be successful in an environment or not. Or my ability to wiggle my ear a little bit is going to change my success in an environment or not. Thus, when we have things like that, there's sort of random changes that can happen in a population that really don't contribute or hurt the success. But continuous traits are far more sensitive to that. Those are the real markers as they change that are really providing the adaptation for individuals. And that's really why we follow them the most. Okay, so I'm going to end this right now. We'll go on to the next lecture later.